be with us today. Just a little bit about his background. He got a PhD from Stanford University in 1986 in electrical engineering. Then he went to Bell Labs, where he did some really interesting work on communication systems, and he was there for a good 10 years, from 86 to 96. In that period, he got the IEEE Baker Prize. This is sort of the prize for the best original work in all the IEEE journals, transactions, proceedings of the IEEE, and so on in 1992. In 97, he went to University of California at San Diego as a professor of electrical engineering, where he is today. And he works on various aspects of information theory, and he teaches information theory, discrete mathematics, algebraic coding, and so on. And today he's going to talk to us about vector quantization.
Okay, thanks. So first I should apologize for my casual attire. My nicer clothes, I think, are visiting Washington, D.C. right now, but I'm not sure. Okay. Okay. So I'm going to talk about scalar and vector quantization and the advantages of vector quantization, and what's the connection to speech. I think there's sort of a Markov chain from this talk to quantization to speech. Okay, so if you think quantization is closely related to speech, this is too. All right. Okay. Right. So let's start with a very basic introduction. Actually, the whole talk is going to be very basic. Let's talk about source coding, which is the simplest problem in information theory. You have an alphabet source, let's say x, and you have a probability distribution p over that alphabet. Okay, and a source is just a random variable which is distributed according to this probability distribution p. Okay, and your goal is to reproduce x, or to describe x exactly, to describe what the value of x is. Okay, and you ask what is the number of bits that you need to do that. Right? Everyone familiar with that question? Okay. Right. Now you can talk about coding a single instance of x, and that's what we call scalar coding, or coding a large number of copies of x, which is called block coding or vector coding. Okay? So when you talk about scalar coding, you want to encode just one instance, and then in the worst case, you need log of the number of values that x could take, log of the cardinality of the support set. Let's assume it's distributed over all x. And the expected number of bits you need is somewhere between the entropy of x and 1 above that, and you can achieve that using Huffman coding. Right? Okay. Now, so now you can say, okay, what if I don't insist on coding one element, but I'm going to wait till I have a number of x's and encode all of those together? Can I save? Right? And so you look for a sequence of independent copies of x, and you ask how many bits do you need in the worst case per instance now, and how many bits you need on the average. And in the worst case, you need log of x. Instead of the ceiling that you had, you just need log of x, because it's going to be the ceiling of log of the cardinality raised to the n. You take the log of that, normalized by n, the ceiling is going to go away. And the expected number of bits is exactly the entropy. Okay? So the conclusion is that you, if you ask, did I save much, then the answer is no, you saved only less than 1 bit. And the only reason you did that is because of round-off errors, because here you need to just, this is an integer, you need to round it off to the next integer. So basically you save nothing. Okay? But that's when you want to reproduce x exactly. Okay? Now you can ask what happens when you want to reproduce x approximately, and that's what's called, that's what's called either rate distortion if you're talking about the theoretical aspects of vector quantization, if you're talking about the practical aspect. So again, you have an alphabet x, you have a probability distribution of the alphabet, and you have a random variable distributed according to this probability distribution that's exactly the same as before. Okay? But now instead of reproducing x or describing x, you want to reproduce an approximation of x. So you assume that you have a reproduction alphabet x hat, which may be the same or different from x, and you have a distortion measure between elements of x and between x and its reproduction, which takes any two values, x and what you reproduce it as, and maps it to some distortion. Okay? So standard distortion would be distortion between x and x hat would be the absolute distance between them, or the Euclidean distance, and so on. Okay? Just natural things. Okay? And you allow yourself some distortion value d, and you ask, what is the number of bits do you need to reproduce x as x hat, such that the distortion between x and x hat is less than d. Okay? So if you let d equal 0, then you're back to the original problem, because then you allow yourself 0 distortion, and you want to reproduce x exactly. All right. Now you can ask, why should we allow this distortion? So sometimes the exact precision is unnecessary. When people describe temperature, temperature is a real number, but usually they just say the temperature is like 80 degrees or something, or 81 degrees. So we don't care about the actual number. Sometimes you can describe a number precisely, even if you wanted to. For example, if you have a Gaussian distribution, you can describe it exactly, because that will take infinite precision, will take infinitely many bits. Okay, so you need to describe it to within some precision. And if you allow any kind of precision, then you can get it to a finite number of bits. Okay, and also maybe you can even describe it precisely, and precision is necessary, but you also care about bits, so you want to save bits. So there are several reasons why to do that. And why do we have a reproduction alphabet which is different from the original alphabet? Because sometimes you want to reproduce the input in some smaller alphabet, like reproduce temperatures as integers, so x hat is going to be the set of integers. And sometimes you can get solutions in an alphabet which is different from the original alphabet. For example, if these were your points, and the distance, let's say the distance was 1, 1, 1, and you wanted to reproduce them to within 0.9, then if this is our alphabets, these 4 points, then representing them as one element here will represent one accurately, but the other ones will be with large distortion. But if you represent them as a point here, then you'll roughly 0.7 from each one. So now you reproduce each of them as this single point, and there's some advantage to allowing other points. So that's why people usually say we have reproduction alphabet, which is not necessarily the same as the original alphabet. Okay. Now, the variations on the problem, which is you can ask about the number of bits you need in the worst case and the average, just like in the standard source coding case. And you can ask about the worst case distortion or the expected distortions. Okay? And I'll try to stay away from these issues, just be more general. Okay. Any questions so far? Yes.
I'll address later because I forgot it.
Okay. Yeah, but any questions anytime, no problem. Okay.
I got it.
Yes. All right.
How, let's say somebody feeds you 87.2 and you only want 86, 87, 88. How do you lose the bits in the decimal and not in the like 87 itself?
Okay, so the way the problem is defined is someone tells you, this is my distribution. Okay, I have a Gaussian distribution, and I want you to reproduce it to within 0.65. Okay, and so what you'll do if this was a line, then one thing that you can do is you can quantize the elements to things that are 0.65 times 2, which is 1.3 away. Okay, so you're quantizing to 1.3, 1.3, and you represent any element in this area as this point. So you know you'll be within 1.65 away. And that's why this problem is called quantization, because you quantize all these values to this one, you quantize all these values to this one, and all these values to this one. Does that, yeah, I'm sorry.
So depending on your problem, the quantized version could be 87.25 and not 87.2, because that might be the nearest representative value, depending on how you chop it up.
So between us, you got your answer?
Okay.
Yeah? All right. Okay. Okay. So also for this problem of reproduction with distortion, you can talk about scalar quantization and you can talk about vector quantization. Scalar quantization is what I drew here when you just quantize one element. Just you give me a number and you want it quantized, okay? And we call it R1. R stands for the single element that you're quantizing. Is the number of bits that you need for one instance of x to reproduce it within distortion d. D is your 0.6, whatever your distortion that you're getting, okay? Or I can wait till I get a whole bunch of them and quantize them all together, and then I'll let Rk to be the number of bits I need for k independent copies of x, okay? And then I'll define R of d to be the limit of Rk of d. I normalize by the number of instances, and I let this go to infinity, and that's what I call R of d, the number of bits I need if there's no restriction. Okay? And the natural question is, can R of d be much smaller than R1 of d? Can you save by encoding many things together? Okay? Which for the previous case, when d was 0, we saw that you can only save the round off, right? I mean, just, okay. Okay, and what we'll show is yes. The answer is yes, even if x1, x2 are independent, as we're assuming. If they're not independent, if they're dependent, then of course you can save because you can just encode the first one and encode it 1 billion. Okay, so there's nothing to be said. But even if they're completely independent of each other, and even if you let the distortion, so we didn't describe what the distortion is. Remember I said that's one of the variations, so we'll take the harder one. The distortion between a collection of, if I give you x1 up to xn and the reproductions, and I let the distortion define it to be the maximum of the distortions. The reason this is more difficult is because maybe if I define it as an average, you could say, okay, maybe you can do something, you could save because maybe one of the elements had a high distortion, but you're saving on the other one. So I'm going to look at the worst distortion. I want all of them to be less than my d. So I'm going to define distortion to be the max of all of those, and I'm going to count the worst case number of bits. So again, I cannot save by saying, okay, when you have a large number of elements, maybe they even out on the average. So I'm going to look at number of bits in the worst case. You can have, even with all these things, you can have an arbitrary discrepancy between the number of bits you need for one instance and the number of bits you need per instance when you encode a block. That's what we're going to show. So, what, clear? Okay. So what we're going to show it using a simple, probably the simplest example you can that shows this stuff, and may look unrelated, but it is not. Okay, and it shows that if you describe a number of independent, yes?
Can I understand the claim? So what you're
Absolutely.
saying is that when you say it can have arbitrary discrepancy, are you implying that you can cook up a distribution for which RD can be 1/10 of R1? If I say I want it to be 100, you cook up another distribution where it will be 100th of R1.
It's correct in more ways than you think. Yes, everything you said is correct, and the crucial word is cook up, actually. So it's not going to be true for any distribution. So for example, for this one, there's clearly a distribution where you cannot save, right? I mean, if I told you it's uniform from 0 to 1, and I want to describe it, there's nothing you can do because the problem is just very symmetric. But you can cook up a distribution, can come up with a distribution for which, if you tell me I want something where to describe one thing I need 1 billion bits, and to describe things when I encode a large sequence I need 0.0001 bit per instance, I can come up with that. But it will be a contrived distribution, you're right. But what it shows is there's something to think about here, that in some cases there is reason to go into vector quantizations, maybe others there's not. And an interesting question would be, when can you save and how much can you save? But at least it shows that you can save a lot. Okay. Okay. So so this example that we're going to look at is a mail order example. So think that there's a mail order firm, and they sell shirts, okay, and they have N shirts in their catalog. And they've done this for a while now, and what they've seen is that every customer likes exactly M shirts out of the N and wants exactly one. It doesn't care which one. So for example, a customer, they have like maybe M blue shirts, and a customer wants any of the blue shirts, doesn't care which one. Or a customer will want any of the M striped shirts or any of the M t-shirts, okay? But doesn't care which one he gets, okay? And what they want to do is they want to design an efficient form such that the customer can send very few bits and be able to get the shirt that the customer wants, okay? Right, so let's do a few examples. So first of all, let's say that M is 1, namely every customer likes exactly one shirt out of the N and wants to get that shirt. How many bits would the customer need to transmit? I'm sorry? M is 1. M is 1. So every customer comes to the storefront, to the website, and sees one shirt that he likes out of the N, and he wants to get that one shirt. He wants to make sure that he gets that one shirt. How many bits does the customer need to transmit? So just for, actually all you need to know is here. You have a mail order firm, they have N shirts, and they know that every customer likes M, let's say 5 shirts, and wants to get one of them, doesn't care which one. The question is, how many bits does the customer need to transmit to get that one shirt out of the 5? Okay, so if the customer likes exactly one shirt, he needs to specify that shirt, right? There's nothing you can do, right? I mean, so you need log N. Because he must specify the shirt, okay? Now, what if M is N, every customer likes all the shirts, how many bits does the customer need to transmit? 0, right? I mean, doesn't need to say anything, they'll just send him any of the shirts that they have and the customer will be happy, correct? So let's look at the first interesting case. what if every customer likes n minus 1, almost all the shirts, except one. So now it cannot send anything because it's taking the risk that they're sending the one shirt that it doesn't like. How many bits do we need here? Okay, log n would do. Can you do with less, with maybe even slightly less? Okay, you can you do with, I shouldn't say slightly, can you do with a lot less? Okay, so every customer likes almost all the shirts, all of them except one. So there are two possibilities. Either the customer likes shirt number 1, right? And if it doesn't like shirt number 1, then he likes all the others. So what can you do? You can just tell him if he likes shirt number 1. If he likes, he says, I like shirt number 1, and then they'll send shirt number 1. Or he says, I don't like shirt number 1, and then they'll send him any of the other ones. Right? Okay. So is that clear? So you need only one bit. Just, do I like number 1 or do I not like number 1? Right? Is that clear to everyone? Yes.
So are you saying it's not necessary that the customer be able to fully express his preference?
That's correct, because the customer likes all blue shirts and he wants to get one of them. As he said, it's a cooked up example. So, right. Yeah, so he likes all M shirts, doesn't care which one. So he says, I like shirt number 1, then he'll get shirt number 1. Or he says, I don't like it, and then he'll get one of the other ones, and he likes all of the other ones. Okay? Right. Now, the question is, in the general case, what happens? And the answer there is that you need, we'll prove it, that you need log of n minus m plus 1. So you can check that when m is equal to 1, you get log n. When m is n, you get log of 1, which is 0. And when m is n minus 1, you get log of 2, which is 1. Okay, so that's the general answer. Okay, we'll go over it. Okay, so we'll prove the upper bound. We'll prove that the number of bits you need is less than that number, and we'll show that it's at least that number. Okay, and all this time I'm writing 1 because this is a single instance. Okay. Right. Okay, so how can you achieve this log of n minus m plus 1? So what they do is they agree in advance. Remember, n and m are known. So when they design, they know n and they know m. They agree in advance of protocol where the customer, what he does is he says, he looks at the shirts that he likes and finds the lowest index and says, the lowest index of shirts I like is, and then he just says that number. Okay? Okay. So now, does it work? Yes, it does, because he'll tell them an index of a shirt that he likes and he'll get that shirt. And the question is, how many bits do you need? So you need log of the number of values that this lowest index could get, right? So this lowest index could be 1, and what's the highest value it could get is it's n minus m plus 1, right? Because the highest value would be if the n shirts, n1, the highest value is if the shirts that he likes are all the m shirts on top, right? That's the highest value that the lowest index would get. So the m shirts here, those are the one he likes, and those are the one he dislikes. There are n minus m shirts here, so the lowest index is this one, which is n minus m plus 1. Okay? So the lowest index can be 1, and it could be all the way up to n minus m plus 1, cannot be higher than that. Okay? So the number of bits you need is log of that number, log of n minus m plus 1. Is that clear? Yes? Not so? Yes?
But he doesn't have to like the last 10 shirts, right?
No, but that's correct. He'll look at the set of shirts that he likes, and he'll find the lowest index, and he'll just tell him what the index is. That's the protocol. So and they'll send him that shirt. So he's guaranteed to get it. And now the only question we want to answer is how many bits does he need to send? So we're looking at what values he may possibly send. He may send number 1 if the lowest index is 1, but he will never send n, right? Because he likes m shirts, so the lowest index will never be m. And what we showed here is the lowest index, the most it can be is n minus m plus 1. So he sends a number in the range from 1 up to n minus m plus 1. So the number of bits you need is log of that range, which is less than log of n. Right? Sorry.
How many shirts does he want again?
He wants m. He wants m shirts. Let's think of m as being 10. Okay? Then the lowest index that he could possibly, he'll send the lowest index. It could be 1 if the lowest one that he likes is 1. But the highest number he'll send is n minus 9. right?
But how did you set up the arrangement of the shirts in such a way so
Oh, okay, they agreed on a numbering of the shirts. They show the shirts and then show the numbers of the shirts in the catalog. He looks at the shirts that he likes, and he sends the lowest index of all those shirts. Yeah, you're right, they agreed on that in advance. Does that make sense?
Yeah.
Okay, is that now?
Yeah.
Yeah? Okay, so normally this would be the more interesting part because this is the constructive part, and the part where you show that you need that many would not be interesting, but here I want to concentrate actually on the lower bound. And the reason is because I want to show that for one, if you're just selling shirts, I want to show you cannot do any better than that. But I want to show that if you sell shirts and pants and shoes, which I'll need soon, then you can, even though there's completely no relation, you can still, you can save. Okay, so that's the part that I want to make sure that you agree with. Okay, yes?
Don't slow this one down.
No.
Suppose I like the first shirt.
Okay,
I send you one.
one, right.
How do you know which M-1 remainders to sell them?
No, okay, so we agree that M, let's say M is 10, and N, let's say, is 100. And let's say you like shirt number 1, 5, 9, and 29, and so on, and there should be 10 of those. Okay, so, and so on up to 75, okay? Then you send me index number 1. I'm going to send you shirt number 1. And so, which is one of the 10 shirts that you liked?
Oh, I'm only, I thought it was,
No, you're only looking for one shirt out of the, you want a blue shirt, and you'll get one. Or if you want a striped shirt, you'll get one. Okay, is that? Okay, okay.
So there are M he likes, but only one that needs to be delivered.
He's only
Correct.
buying one.
It's only buying one. Thank you. Yeah, I'm sorry. Yeah. Obviously, I'm not practicing what I'm preaching, which is shorter description of a problem here, but a short test. But okay, as long as you eventually, all agree. Okay. So what we want to show is that you need log of n minus n plus 1, and the way we'll show it is by showing that if you give me any valid protocol, then the number of messages that must be transmitted is at least n minus n plus 1. Then the number of bits we'll need is at least log of that, which is what we want to prove. Okay? So I want to show that no matter which protocol you show me, the number of different messages that I could possibly send is at least that many. Okay? And then we'll be done. Does that make sense? Okay. So how do those protocols work? Okay, the way they work is this. No matter how you come up with the protocol, I'm going to transmit you some sequence, 0, 1, 1, and then you send me shirt number maybe 7. Or maybe if I transmit 1, 0, 1, you'll send me shirt number 19. And 1, 1, 0, you'll send me shirt number 15, and so on. Okay? And maybe for 2 different numbers, you'll send me the same shirt, which means you didn't design a good protocol, but it's okay. Okay, so but the point is, for every message that you send me, there is exactly one shirt that I'm going to send you. Okay, that you'll get in the mail, right? If I hear 0 and 1, I'm just going to look at send you whatever we agreed on. So shirt number 7. Now suppose that there are strictly less than n minus n plus 1 messages that I can possibly send. For example, here there are 3 messages that I could send. Okay, so namely they are less than or equal to n minus m. Less than or equal to n minus m messages because it's an integer, right? That means that the number of shirts that you could possibly get is at most n minus m, right? But that means that if the shirts that you like are the remaining m, you'll never get one of those. Because there are n minus n possible messages, therefore there are n minus m, like 7, 19, and 15 possible shirts you'll get. If the shirts that there are m remaining shirts, because these are n minus m, and there are m remaining shirts. And if you like exactly the remaining set of m shirts, you'll never get one of those no matter what you send. So you'll never get the shirt that you like. So what that shows is that you cannot have less than n minus m plus 1 messages. You have to have at least n minus m plus 1 messages. And therefore the number of bits is at least log of n minus m plus 1. It's crucial that you agree with that. So, let's do an example. Okay? So let's say that there are 7 shirts. There are 7 shirts. 1, 2, 3, 4, 5, 6, 7 shirts. And we know that you always like 3. Okay? So the claim is that you need at least 7 minus 3 plus 1, which is 5 messages, and we want to show that you cannot construct a protocol which has only 4 different messages. Okay, so let's say you constructed a protocol that has 4 different messages, 0, 0, 0, 1, 1, 0, 1, 1. Okay, when you tell me 0, 0, I'm going to send you one shirt, right? Some shirt. Let's say, it doesn't matter. Let's say I should send you this shirt. Okay? When you tell me 0, 1, let's say I send you this shirt and this and so on. Okay? Now, you notice that there are 4 different messages. No matter what you send me, you'll get one of 4 different shirts, right? Now, what if you happen to like, remember, m is equal to 3. What if you happen to like these ones? Okay, you'll never get those. If you send me 0, 0, you won't get it. If you send me 0, 1, you won't get it, and so on. Okay? So the reason is because the number of messages was smaller than n minus m. So the number of different shirts you could get was at most n minus n. And they could potentially not include the m that you like.
So basically, there is an x for which b of x hat exceeds the distortion.
Yeah, but I don't want to think of this as a distortion problem yet, but potentially, you may be right. I'm not even sure. I just want to think of it as this. But is that clear? Everyone agrees? Yes.
That sort of assumes that you don't know your customer, right?
No, you don't know. You know. Okay, you know your customer to the extent that you know that they'll always like exactly M shirts. That's the problem.
Well, I mean, it's an anonymous customer. You
Right.
don't know it by number. You don't have a relation. I mean, because it might be able to do better if you know that it's coming to customer.
Yeah, we assume that, okay, in all these problems, we assume that there is some probability distribution, right? But there's some randomness, and the randomness in this is exactly which shirt the customer wants. I mean, if you knew that you always like the same shirt, then you'd be able to do more. Is that? Okay, but everyone agrees that you need log of n minus m plus 1? Okay, that's the only thing. Okay. All right, okay, so to conclude, we know that the number of bits is exactly that, so it's easy to determine the number of bits you need for selling a shirt. So now let's look at what happens when you have multiple mail orders. So now the company sells, in addition to shirts, they have K product lines. Maybe they sell N shirts and M pants and M shoes, and the customer likes M of each. So the customer comes to the website and he likes the M blue shirts, and he wants to get one of them. He doesn't care which one, and he likes M, khaki pants, and he wants to get one of them. He doesn't care which one. But there's no relation between the shirts that the customer likes and the pants and the shoes. This could be any subset of M, any subset of M, and any subset. Okay? And the question is, how many bits do we need now? Okay? So clearly you can do with K times the number before, right? I mean, you can just say describe which shirt that you want and describe which pants and so on. The question is, can you do better, even though there's completely no relation between the shirts and pants and so on? And what we'll show is that, yes, even though the different lines are completely unrelated, it's just, they could as well be in different companies. The number of bits is this number, which typically is much smaller than K times the original one. Yes?
Well, if you took your previous protocol, couldn't you take a maximum of those? You take the least number of each one you like, and then take the maximum.
Okay, but the maximum could also be the same number, right?
Yeah.
So you, right? Okay. Okay. So, all right. But that's a good suggestion. Right? Okay. So can we do better? And the answer is yes. And then you get these two ugly numbers, which right now you probably can't see that one is better than the other, but it is. But we'll go with it. Okay. All right. Okay. You can see a little bit because this is the largest term here is k log n over m, and here it's k log n minus m, and so n over m can see can be much smaller than n minus m. But we'll get a little bit of intuition. Okay. What happened? Okay. All right. Okay. So to get some intuition about these numbers, we'll take m, which is n over 2. So every customer likes half of the shirts and half of the pants. then to get, for exactly 1, you need log of n minus n over 2 plus 1, n minus n plus 1, which is log of n minus 1, essentially. Okay? So we said that one line requires at least log of n minus 1 bits. You agree with that? Because you get here log of n over 2 plus 1, it's bigger than, right? Okay. So if you have n over 2 shirts, you need log of n minus 1 bits. Okay? Now, if you plug in k equals 2 in the previous formula, you'll get your 2 log n over 2 plus log n plus log 2, which is what I wrote here. 2 log n over 2 plus log n plus log 2, which gives you log n plus 3. So you see that for pants and shirts, you need at most 4 additional bits. So you can get the second completely unrelated line for just 4 bits. In fact, 2 bits would do, but this proof just gives you 4. Okay? And then if you look at the original formula from the previous page, you'll see that it gives you k log n over 2, which is k plus log n plus log k. If you normalize it by k, you'll see that multiple, if k is large, the number of lines you have is large, then you need 1 bit per line, because when you normalize by k, this term is going to go to 0, this term will go to 0, and you'll be left with 1. Okay? So what this tells us is that even though you have completely unrelated instances, describing one will require log n bits, which could be as high as you want, but describing many will require only 1 bit per instance, even though they're completely unrelated. Okay? So does, actually, do people see how to do that? How you could get something like that? Yes?
Maybe by relating to the first example, let's say you might go to the first time, the second time you somehow relate to the first one.
But
the same or different. And then
okay, so the first time, okay, so let's say you conveyed the lowest index and you got your shirt, and now you want to say, is it the same or different? Let's say if it's the same, you're in luck, and that's okay, but if they're different, you still have, you reduced one, and you still don't know. Well, you can reduce all the, the lowest, so you don't want the ones below that. And to be honest with you, actually, I think if you do it sequentially like that, I don't think you can save. So even though I don't see why this would work, I think you need to design them together. It would be interesting if you can design a protocol where you can say which shirt you want, and then count on what you said, and then do the next one. I suspect that you cannot. I suspect that you need to know in advance which shirt and which pants. But it's interesting if you could. I don't know that you cannot, but. Yeah.
Somehow you are reusing, you have these independent things,
right,
and you are reusing the coding of the first.
Right.
You are taking advantage of some coding here to add some little information from the second one and from the third one. And so on.
Right.
And you are reusing.
Right.
But I don't know how.
Does the order control the order of the product lines?
Yeah, so that you don't want to get the shirt that you like in the pants, right? I think the answer is yes, if I understand your question.
In other words, you follow a protocol where you might select the pants before the shirt, and then.
In this case, you'll send them one message, which will be a little longer. It will be that long. It will be that long, long n plus 3 bits, and then they'll send you a pair of pants and a shirt. Yeah, but you tell them together. You send them this many bits, and they'll send you 2 things in the mail. And the shirt will be one of them you liked, and the pants will be one of the pants you liked. Yeah. Yeah.
Like if the shirts are the first 4 and the pants are the next 4, and let's say you wanted shirts 1 and 4, then after you order those 2 shirts and you want to order pants, couldn't, instead of saying I want number 5 being pants, you can say I want number 2 being like, since we know it's not shirts because we go in order, it must be the first pair. The first pre-shirt label still left belongs to the first pair of pants?
You could, but you see the 2 sets could overlap because there's no relation. They could overlap, so you don't know that they're disjoint. Okay. They could overlap. They could even be the same, or they could be completely disjoint.
Supposing you took the lowest number for the shirts, and then you take the closest number to the amount of pants, and then you'd send the amount has to be added to the number for the first one to get the pants.
Okay. So that would fall in the same framework as the framework that Igor was talking about, which is you encode the first one, ignoring the fact that you want another set, and then you'll encode the next one, right? You could, and I suspect, I don't know, I suspect that these methods will not work. I don't know for sure, but I suspect that if you come up with a scheme that you first just describe what you want for the shirts, and then you would describe what you want for the pants, I suspect that they won't work. So specifically for your method, I think you could come up with, you know, like something where you like these ones, and then the one that you like will be very far away. But I don't know it for a fact. I'm concerned. I think that all these methods are not going to work. Okay, so I'll show you the only one case where I can explain things easily. This is this one case, and the others I just have a proof, and I can't explain it easily. So think of n being odd, although that's not crucial. The only thing that we'll care about is that m is bigger than n over 2. But just to make it nice, I'll make n odd and m be just slightly bigger than half n. Okay? So the only thing we care about is that m is bigger than n over 2. Okay? So in the case of one product line, we need log of n and n plus 1 over 2, right? I'm sorry, we need the number for n and n plus 1 over 2, which is log n, it's this number, n minus n plus 1, which is bigger than log n minus 1. You agree with that? Okay. So I want to make m bigger than n over 2 for the rest. And I want to make m closer to n over 2 because I want that for one instance I need many bits. So we know that when m is n over 2, I need log of n minus n over 2, which is log of n over 2, which is log n minus 1. So it's a lot of bits, right? If you look at the number of bits that you need, this is n. It can go, I'm sorry, this is m. It can go from 1 up to n. Then when m is 1, I need log n. And it will go down, it goes like log of n minus m plus 1. So if I get here m, which is n over 2, I get here log of n over 2 plus 1, log of n over 2 plus 1, which is roughly log n minus 1. Okay, so that's what I did. I chose m to be roughly n over 2, so I need at least log n minus 1 for one instance. The interesting part is that because m is bigger than n over 2, there is a very, very simple protocol that will allow you to get this, to get both your shirts and your pants. Okay? And the reason is that if you look at, this is your family of, and this, you look at the subset, just the indices, okay? So let's S be the set of, S is the set of shirts that you like. And we know it's bigger than n over 2, m, which is bigger than n over 2. And let's look at the set of pants that you like. Also bigger than n over 2. Okay? So we know that they must intersect. You agree? So if I look at the shirts are like number 1, 3, 7, look at the indices, there are like more than half the indices, and I look at the pants I like, the indices, there are more than half the indices. There must be an index of pants and shirts that I like. So the set of shirts that you like has cardinality bigger than n over 2. The set of pants that you like has cardinality bigger than n over 2. They must intersect. There must be an index of both shirts and pants there, okay? So what I can tell you then is just send me shirt and pants number I. So I give you this one index, number 7, and say send me shirt and pants, number 7, and you send me the same. And I only describe one number. So the number of bits I needed was less than log n. Just 1 second, okay? So you notice that for, just to tell you the shirts, I need at least log n minus 1. That's this number, that's what we saw. And for, to send you this number, I needed to most log n sinning. So I should have written 2 to be fair, because there's a sinning. But it's most 2 bits and most likely 1 bit, additional bit. Yes?
So how did we know that we like more than half the shirts?
The assumption is that n and m are parameters are known in advance.
But for the first example, the one where you only like, there was only one item, n didn't have to be greater than n over 2.
No, that's correct.
But for this one, you do have.
Okay. For me to be able to explain it to you easily, it has to be. Otherwise, I don't have this intersection, and then I have a proof.
But it's not true in the general case?
I'll tell you. So in the general case, we have the complicated formula, but I don't have that I showed you, and I'll show you again. But we don't have. I don't have an explanation. I just know that it works.
So you're saying you don't have a constructive proof?
Correct. That's correct. Actually, that's what the next step is. says that for the general case, there's a probabilistic proof that shows that something exists, but there's no efficient constructive protocol. Yeah. Right. Okay. Yeah.
So you don't know how to, you're going to give us a formula, but you don't know how to realize.
That's right. I'll give you a formula and maybe a little bit more than that. I'll tell you that I'll give you a way to construct a protocol, and I say if you select a protocol trend, then most likely it will be good. I mean, most of the protocols you could come up with that way, the way I'll give you will be good. Okay. Yes.
Can you go back, please?
Absolutely. If you want, we can do an example. If that, or let's take n equals 9. Take n equals 9, and m equals 5. So n is slightly bigger than n over 2. Okay. Okay. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the shirts. And then you have the same thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? Now, in order to describe one of those, you need log of 9 minus 5 plus 1, which is log of 5, right? Meaning you need to send 5 different messages. Likewise here, in order to describe this, you need log of 9 minus 5 plus 1, which is, again, log of 5, okay? But so if you wanted to do them independently, you need log of 5 plus log of 5. But in fact, which is log of 25. Okay? But in fact, if you send me just one of, not 25 messages, but one of 9 messages, that's enough. And the reason is, if you give me any subset here of size 5, 1, 2, 3, 4, 5, and any subset here, those are the shirts that you like, and these are the pens that you like. Okay? There must be at least one index, in this case 7, for which you like both shirt and pants. So you just tell me, send me shirt and pants number 7, I'll send you the same one. Okay? And so it's only 9 messages compared to 25 messages which you would need. Yeah? Yes?
No, but when you design the protocol, how do you know the 7 is included in the protocol?
You don't, but you know that there will be a shirt that when you look at the set of indices of the shirts that you like and the set of indices of pants that you like, you know that there will be one which will be shared between them. In this case, it's 7, right? I don't know that in advance. So you just tell me, send me this one index.
Yeah, but how do you know you can describe this index? Because you don't know ahead of time which index to...
That's correct. But so to describe this index, you need log of the number of log of n, log of the number of possibilities. So in this case, the customer. This is how you describe your form.
No, but when you assign the indices that you can send, you don't assign all the 9 indices, right? You can only send 5 different indices.
No, in the new protocol?
Yeah, in the new protocol, I can send 9 because you'll tell me which ones you like. So you'll send log n bits. I'll give you enough space to this. Yeah,
I understand.
I'll give you enough room in the form for n messages. So the point is, instead of having n over 2 square, which is the number of messages you need before, now you just have n different messages. Clear to everyone? Okay. So as we said, the general case, we don't, there isn't simple protocol. And actually, this example is not just specific to m being bigger than n over 2. It's also only specific for 2 lines. So if you get more than 2 lines, then this doesn't work. So it's just a fluke that you get this explanation. Okay. Okay. And how is that related to vector quantization? You can use this example to. So now we're going back. Right? I want to keep it as simple as possible. So you let x be the collection of m element subset. This is your alphabet. You let x hat, I wrote y, but I should have written x hat, to be the set 1 up to n. You define your distortion between x and y to be 0 if y belongs to x, to be infinity if y does not belong to x. And then you play with the parameters with n and m, and what you get that you can get arbitrary discrepancy for every delta that you give me, however large, and every epsilon positive that you give me, no matter how small, let's say 0.001 and delta is 1 billion, I can find a quantization problem such that to describe 1, you need at least this billion bits, but if you allowed quantization of many things together, even though they're completely independent, unrelated to each other, and even though the distortion, you're looking at the worst case distortion, and the worst case number of bits, you need at most epsilon. Okay? And this results apply to the worst case. For the average case, it's still unknown what's the largest discrepancy that you can get. I can show that you can get a logarithmic discrepancy, but I don't know if you can get an arbitrary discrepancy. I suspect not. And it's related to graph entropy and chromatic entropy, and I think there's some interesting stuff that's going on there. But I still don't know the answer.
I had a question about the problem statement.
Yes.
You had a distortion function which was 0 and infinity.
Correct.
I haven't seen the proof, so I'm just trying to guess that infinity is critical to the proof, right? If I had a big D, a finite D, then does the statement just change to saying that the distortion can be made as arbitrarily close to D, or in other words, will it then hold that R1 could be arbitrarily close to D?
It depends. If you're looking at worst case, like we're looking here at worst case distortion,
right,
then it doesn't matter. You don't need to have infinite distortion. It just makes it easier to describe it here because. Okay.
Because when I saw the result in your abstract, I was wondering, infinite distortion is sort of a extreme case.
Right. Yeah.
And
so it depends. You see, when you move from one instance to many instances, you need to specify some things. Are you going to count expected number of bits, and then how do you define the distortion? We give you two sequences. They define as the average distortion. Do you want the distortion on the average to be at most this D that you gave me, or do you want in each component to be D? Now, if you want it to be in each component to be D, that's more difficult for the vector quantizer because it doesn't have the freedom of making some distortions high. And so we're making it here difficult for the quantizer, for the vector quantizer, because we want in each coordinate to be less than D. And then it doesn't matter if you put infinity, because I could put it like, just above whatever you allow me. Yeah? Okay. So I think that covers what I want to say. And the only thing is, if you want, I didn't try it here, but I can show you how the proof goes. As I said, it's a probabilistic proof, and I can do it on the board if people are interested.
I would like to see the proof.
Okay. Or if people have any questions, then we can also do that.
Okay, why don't we do questions first?
Okay. All right. Okay.
So are there applications of this to problem solving coding?
Or are there applications of this to coding? I don't know. I think as I said at the beginning, I think that this shows that something interesting can happen, and then the question is, for what distributions? And this happens for a very awkward or very contrived, distortion measure. Actually, is what's important here, the distortion measure. And but the question is, what happens for normal distortion measures? Are there reasonable distortion measures for which you also get large discrepancy? And if so, how fast do you approach, the limit? So I think it's, a first step in looking at this sort of thing. So right now I would say no, currently there aren't any, but maybe if someone could say, for example, for the average, you never save very much, and then the question would be, why use vector quantization? Right? Maybe just use a single quantized scalar. This shows that for the worst case, there is a reason, possibly a reason to use vector quantization. And if the answer was that let's say the average is more important actually practically than the worst case, that for the average there isn't much advantage, which I actually suspect. I don't know if I wrote it, but yeah, so I said the largest discrepancy is logarithmic, and I suspect that's the largest I can find. I suspect it's true. So if that's the case, that shows that maybe there isn't a reason to go into high-dimensional vector quantizers, which are much more complicated. And then that would have applications maybe not just for coding, but maybe also for speech, because this means that you can get close to the regions, to the distortion that you want. This would mean to the regions that you want with very low dimensions. So maybe this would apply, if you're doing, quantized, H&Ms or something, rather than continuous. Then it would tell you don't need to maybe go to high dimensions or that kind of stuff. You can quantize, if you look at it, if you quantize your, let's say you're looking at your Melkepstra, So maybe you don't need to look at quantization in the 39th dimensional space, but maybe in smaller dimensional space and get the same locality, maybe.
But I don't see the connection because it seems that your proof says I can give you, your proof would say to me that I can give you a distribution.
Right.
But suppose I have a problem, how do I know that that
Right,
problem
okay.
is well related to it?
Yeah. I made 7 leaps, okay? So first of all, my proof talks about worst case, and then it shows that there could be a huge advantage to looking at high dimensions, right? Arbitrary advantage, okay? So I changed, just to be able to answer your question in a, I was hoping a nicer way, I changed it from the worst case to the average case, where the largest discrepancy that I know is logarithmic. And in fact, I suspect that that's the most you can get. So if for one instance you require 1 billion bits, then the most I can show that you can, you know, even with my most contrived example, if for one instance you need 1 billion bits for arbitrarily many repetitions, dimensions, you need at least log of a million minus log of a million. That's what I mean by logarithmic. So for the average case, which typically is more important, I cannot come up with an example you can save a lot, and I suspect you cannot. There isn't any. Okay? So that's step number 1. So I'm saying number 1, 2. Number 1, average is more important than worst case. And number 2, I suspect that for average, you cannot save a lot. So let's assume that those two things are correct. Then it would say that there's no reason to build very high dimensional vector quantizers, because you can get almost as efficiently with small dimensions where things are much more efficient and much easier to understand. Okay? So that's for coding. Now I'm translating it another leap to let's say recognition. Now if people build, let's say you build a vector quantizer in a 39-dimensional space, there's a direct relation between the number of bits you need to the number of regions that you have. It's the number of bits is log of the number of regions. So to be within the same distortion, it would tell you could get to be within the same distortion and not increase the number of regions by too much, even doing it lower dimension. So does that? But there are many, many assumptions to get to this conclusion. Yeah.
I guess let me ask a question about the arbitrary advantage.
Yes.
So each of your so your plan for, you're saying that the arbitrary advantage you get is that each of that with your method for vector quantization versus simply using log n minus m plus 1 bits concatenated for each one of the k dimensions.
Right.
And that's the arbitrary advantage you get.
Right.
You
So
can get as big as you want as long as you increase
right.
the dimensions enough.
Right. I was comparing. So for one, you need log of n minus m plus 1. Okay, the plus 1 doesn't matter. And then I was saying if you wanted to do it k times, you need k times this. And then you'll normalize by k. So you'll get, if you just did them independently, you need that many per instance. Okay. But if you knew ahead of time that you had all these things to encode simultaneously, then you need log of n over m plus log k plus log n. And then when you normalize it, I'm sorry, you need that. And when you normalize it by k, this will go away, this will go to 0, this will go to 0. So you'll be left with log of n over m instead of log of n minus m. So it's the difference between n minus m and n over m. And so the difference between log of n minus m and n over m. And I chose m so that m is n over 2. So here I get log of n over 2, here I get log of 2. That's the, but
So what does that have to do with the epsilon and the delta?
oh, okay, okay. So if you give me delta and epsilon, I can find n and m such that this will be bigger than delta, and I can find n and m such that this will be less than epsilon. So I just need to find those n and m so this will be satisfied, and define the distortion the way we mentioned it. Okay. Yeah. Okay. So time is up, and I could do the proof. It's a probabilistic proof, as I said. It's one of those things that some people love it, some people don't, hate it. And in any case, as far as probabilistic proof go, it's fairly simple. But if you haven't seen it before, you'll be a little bit confused. So it's up to people. We could just stay in whoever is interested.
Okay, so here are our constraints. Our lunch is going to be here in another 20 minutes. So I propose we just stay put and see the proof anyway. And
Okay, sure, no problem. And I won't be offended if everyone left, it's no problem. So should we turn this thing off, or?
Sure, and we can get the rest of the lights on.
Okay. 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 So the most confusing about probabilistic proofs is the name, because the name has probability in it, but there's no probability actually in the end result. So there's not, what we prove is not going to be, most likely there is. It's just like the example we had. Okay. But we'll use a probability to prove it. Okay. So first of all, what we should do is try to understand the example that we had before, the simple example first. So the way it worked is this: you had where n was n over 2 and n over 2 plus 1, just bigger than n over 2, and k was equal to 2, namely 2 pens and shirts. That's the only example we could explain, and then let's look at it visually. Okay? So we have here shirts, and we have here pants, and you had a set of pants that you liked, and you had a set of shirts that you liked. Okay? And what we said was that these two sets, if you look at them as subsets of 1 up to n, they intersected. So there was an index that I that belonged to both, and then the firm sent you I and I. So the collection of things that they could send you, potentially they could send you anything in this square. It goes from 1 up to n and 1 up to n. Potentially, beforehand they could send you any shirt and any pants, but what they did was they restricted themselves to sending you one of these n packages. They could in fact package before shirt number I and pants number I, put them in one box, that's this one, shirt number 2, pants number 2, and they'll only send you things on the diagonal. They'll never send you shirt number 5 and pants number 10. Okay? So these are the only ones that they would send you. And what your job is to do is to look at the 10 packages that they have, those packets, and just to say, I want to get this packet. Okay? So you could look at this from that way, right? They decide on a collection of representatives, collection of points, and you just say, I want this one. You know in advance. They tell you these are the only things you have, and you want, and make sure that if you have a set of M pants and a set of M shirts, at least one of those representatives will be good for both. And this is what happens here. So everyone agrees with this picture? Okay, so that's the image that we'll do. Okay, so now what we have is we have multidimensional. We have k dimensions. We have dimension 1, 2, 3, and so on. And you'll have a collection here, and you have a collection here of m, and a collection here of m, and a collection here of m. And so eventually you'll get some k-dimensional box, okay, of things that you like. And you want anything within this box. Just like here you wanted anything within this box. And so it so happens there were many that they could have sent you. But if the boxes were, if the sets were almost disjoint, the sets were like this, the beginning and then the end, then there will be only one point in the intersection, right? Because you'll be getting this, and there will be only one point in the intersection with this point. Okay? So you wanted to decide on a collection of things, or a collection of triples or n tuples, such that any Cartesian product of m by m by m contains at least one.
And so the more general idea would be that you want 2 to the k.
What is R?
This is the rate.
Okay, yeah. Mm-hmm.
You want to choose not necessarily on the diagonal,
correct,
somewhere in that space. You want to choose them so that no matter what subsets the user
right,
chooses,
right,
the cross product
right,
has 1 point.
Right. So what we want is we want alpha points in 1 up to n raised to the power k. Let's call him C1 up to C alpha, such that any m by m by m Cartesian product contains at least 1 point. So then what they do is they package C1, which is shirt number 1, pants number 7, they package and so on, and then actually the client, the customer does the job. He says, okay, I have my Cartesian product, contains this, and okay? Is that clear? So the question is, what is alpha? What should alpha be? And that's the only question. Okay. So what they're going to do is, and that goes back to the design, so what we'll show is that if alpha is large enough, then no matter how, most of the ways that you can select those alpha points will be good. Then namely, any Cartesian product that you're given will contain at least one. Okay. Okay. So we choose. So we haven't found out what alpha is, which we'll do when we're done. But we choose C1 up to C alpha at random. And we show that for alpha large enough, alpha bigger than something which we'll figure out, with high probability, C1 up to C alpha is good. And again, don't let this probability word confuse you. It just shows that most likely what you did is good and will work for any collection. Right? Because we're choosing them randomly, there's some probability that we chose all of them to be the same point, and that's bad. But if you didn't do that, then it's good enough. Then it will work. Okay. All right. Okay. So what is the probability that C1 is good for this Cartesian product, 1 up to m, 1 up to m, and so on? What is the probability that C1 is good for that? That's probability that it falls, that the first coordinate falls within here, the second one here, and so on. So that's going to be equal to m over n raised to the power k. Right? I mean, we choose a point. The whole thing has them as size n to the k, and we're looking at Cartesian products of size m to the k. So it's m over n raised to the power k. Okay, so therefore the probability that C1 is bad, good means it's inside, it represents this set. It's good for this set. Is bad, meaning it does not represent the set, or so on, is 1 minus m over n raised to the power k. Yeah, sorry. 1 minus this, okay? Right. Okay. Okay. So now, what is the probability that the collection, that none of C1 up to C alpha is good, meaning all of them are bad, all of are bad for this set? That's going to be at most, that's going to be, because we're choosing them independently, that's going to be 1 minus m over n raised to the power k, all this raised to the power alpha. It's probability that all of them are bad for this set. Okay, namely, the company is choosing C alpha. They're choosing them at random. They're making the packages ahead of time. So C1 is shirt number 5, pants number 2, they make this box. Okay, and so on. And now we're asking, what's the probability that none of those boxes is good for this, for a person who likes 1 up to m, 1 up to m, 1 up to m. So that's this number here. So probability that the first box is bad for him, which is 1 minus m over n to the k, and the second one is bad for him, and so on. So it's raised to the alpha. Okay. Right. So that's the probability that all of them are bad. It's this, okay? And and that's the same as saying the probability that the collection that they came up with is not good for that, doesn't work for this set. Okay? So now, but we don't need to worry about just this set. We need to worry about all possible sets. So what is the probability that exists a Cartesian product for which C1 up to C alpha are all bad? That probability by the union bound, okay? So this calculation did not depend on the fact that this was this particular set. It could have been any Cartesian product, right? Okay. So by the union bound, it's at most this times the number of Cartesian products. So it's at most, it's less than or equal to 1 minus m over n raised to the power k raised to the alpha times n choose m raised to the power k. Because that's how many, that's the number of Cartesian products. Okay? All right, okay. So if we can guarantee that this number is less than 1, if we choose alpha large enough, so for large enough alpha, this number is going to be less than 1 because this number is less than 1 eventually. Okay, so if we can guarantee that this is less than 1, that means the probability that we are bad, that this collection is bad, is less than 1. That means that with some probability, this collection is good. Namely, no matter which set you give me, there will be an element there. Okay, so the only question is what should alpha be? And so now we just approximate. So now we're going to use two approximations. One is that 1 minus x is less than e to the minus x, and the other one is that n choose m is less than 2 to the n. And with these, we get that this number, this probability of bad, is less.
Oh, you need something that weak, 2 to the n?
Yeah, you could use whatever you want. It won't give you. It won't buy you much. You can do the calculation. Yeah. It won't buy you much. Okay, so the probability of bad is less than, so is less than equal to, I'll just rewrite it. 1 minus m over n raised to the power k times n choose m raised to the power k, which is going to be less than equal to e to the minus alpha. I'm using now this one, e to the minus alpha m over n raised to the power k times 2 to the nk. Okay, and we want less than 1. So therefore, we want that e to the alpha m over n to the k bigger than 2 to the nk. Want. And I'm taking logarithm to the base 2. We want that nk is less than alpha times m over n to the k times log e. And therefore, we want that alpha is bigger than n over m. Again, it's all 1. Bigger than n over m to the k times n times k divided by log e. Okay, log e. So that's what we want. Now, alpha, remember, is the number of points that we have. Now, so this is the number of packages that they've prepared. Now, the customer needs to specify one of them, so the customer needs log of alpha. So log of alpha must be bigger than k log n over m plus log n plus log k minus log e. Okay, so this number is negative, so we can just erase it and not lose anything. I mean, we lose precision. I mean, lose precision, but it's still correct. Okay, so and that's the result we had. So we need k. The number of bits that needs to transmit is k times log of n over m plus log n plus log k, which is exactly the formula that I gave. Okay? So, but as I said, it doesn't show you how to design those points, but it just shows you that they exist. There's another proof that is different, but still doesn't give very much intuition. But there's no proof that I know of that is. Yeah.
But you don't know exactly with what probability that is happening.
That's correct. But that's correct. But if the point is that these numbers go exponentially down. So let's say you found this alpha at which you believe it's 1. It's going to go exponentially fast to the probability of bad to 0 above that crucial alpha. So if you just choose slightly less than that, then most things, if you just choose those points at random, very high probability that'll work. Does that make sense?
Yeah.
You find this limit, and actually, as Sanjeev was saying, we were using very, very weak approximations. But you found those limits, and then if you go anything above these limits, then very, very high probability if you choose those points that work.
I guess you'd be happier if I would have an idea of how small that probability is. You get a bound on that.
Yeah. So if you give me m and n, I'll give you a bound. Right? I mean, yeah. It's just plug in this formula, calculate. It will give you a bound. I just approximated, but if you give me,
For example, for that alpha example,
Oh yeah, then just plug it in. Just plug it in and calculate.
No,
I mean-
I guess the argument that we were here, wanting to hear is that, let's say for a particular alpha, that probability came out to be 0.9, and you wanted that probability to be less than 0.1.
Right, right.
So you
just
want-
have another factor in there.
Yeah.
So say less than 1, you say less than 0.1.
Right, but I'll tell you why I don't get excited about this, because I don't like this whole argument to begin with. It just shows you that you can do it. Nobody's ever going to use this to design a code, right? So the fact that they can do it and succeed with probability 10% or 90%, I mean, if they want to design a code, they'll want to come up with something that makes sense, right? I mean, so yeah, you're right. It would be nice, but it's not anything anyone will ever use anyway.
Seems like you could improve the balance significantly if you, don't assume uniform distribution over the original marginal Cartesian guys.
Okay.
And B, even if you did allow there to be some, I mean, I know you said that you're doing this with the case when they're independent, but
Right.
to allow some dependence,
Well,
would be much.
Yeah, oh, absolutely. If you allow dependence, then there's no limit to how much you can.
But
Yeah,
in the case when you, like this uniform
Correct.
distribution, M over N.
correct.
Would be,
Correct. You're correct.
you need to just try some
Yeah.
distributions.
That's right, but I'm just looking at the simplest thing I can think of, and if it's not uniform, you'll be able to save for the vectors, but you'll also be able to save for the individual in one, so that's why the things will come. It's not like you're saving in just one, you're saving in both, and then you need to compare this after the savings in both. It's a little more messy, but you're right, yes.
Can we look at this result as kind of silver lining inside the test dimensionality that your take advantage of the fact that in high dimensions you're going to, there's going to be a small subspaces there in high dimensional space where most of the mass.
Yeah, so this whole thing asks, is there any reason to get involved with the curse of dimensionality? And it says that under very, very contrived conditions, yes, there is. It doesn't say that under the conditions people usually encounter this, but it says, yes, possibly there is. So, maybe. But yeah, so it sort of says sometimes there is a reason to do it.
I'm very strongly, whatever, I feel that there is a very good connection somewhere to some of these type counting kind of combinatorics arguments, because I'm trying to see if there is any connection that you have these well-defined subsets, and there ought to be one subset of cardinality or whatever, something to the other, which has the right properties. I'm wondering if there is any such.
I'm not sure exactly what you mean, but the whole thing is very combinatorial and is related to a bunch of other combinatorial problems. So
what I'm saying is there a way to get rid of these probabilities and actually?
This you could explain this as a counter argument, but it's just more. If you're in this, if you've done enough, then you're used of those, then you're used to explaining things in terms of probabilities. I could have replaced the probabilities by counting. It's a counting.
There were uniform distributions everywhere.
Yeah,
so
it's a counting argument. It's a counting argument in disguise. But people usually use the probabilities because all the numbers are less than one, and yeah. But it's just a counting argument. Yes, you're right. Yeah, it's here this bound. What did we use? We used the union bound. What did we use probability? We used the union bound. That's just saying that the cardinality of A union B is less than or equal to the cardinality of A plus the cardinality of B. And instead what we use is the probability of A union B is less than or equal to the probability of A plus the probability of B. Okay? So if you replace this by this, you don't need this argument. Now we also use the probability that if you choose, here, when we move from 1 to all of them, we use it's this. But that's again is you look at the number of ways that you have a collection of elements, one in each, and one you ask how many are good for this and that, and that's just the product. That's how we get this. So you can replace all of those by counting arguments. We just this whole culture with just people with probabilities. Yeah. Yes.
I guess this is probably a really simple question, but what does it mean for the probability that the Cartesian product is bad to be greater than 1?
It will never be. Remember, this is okay. We have an upper bound. No, you're right. So you are saying, what if you get a number bigger than 1? Should you be troubled? The answer is no. What we calculated here is the upper bound. This probability will never be bigger than 1, as you can see, because this number is m is less than n. So this number is less than 1. Therefore, this number is less than 1. This number will never be less. Will never be bigger than 1. So probability laws are not broken. But now we made an approximation, we use the union bound, which is just an upper bound. That number, now that number could be bigger than 1, but it's just an upper bound on the probability. The probability itself will never be bigger than 1. Yeah. Right?
Thank you.
Okay, thanks.